Good morning, professors. Good morning, Subbulakshmi ma'am.
Good morning, ma'am.
I welcome you all for the third day of session 1 of this FDTP. So, about resource person, Dr. Subbulakshmi P, Assistant Professor, School of Computer Science and Engineering, ADT University. So, she has published more than 14 articles in conferences and 12 in journals. And her areas of interest are cognitive networks, wireless networks, game theory, and big data. I welcome you for this FDTP, ma'am. So the session is all yours, ma'am. You can start your session, ma'am.
Yeah, thank you so much. Good morning, everyone. I hope my audio is fine, right, ma'am?
Yeah, ma'am. Yeah, it is clear, ma'am. And
Ma'am, is my screen visible?
yes, ma'am. It is visible, ma'am.
So the PPT is visible, right?
Yes, ma'am.
Very good morning, professors. So the topic ADT, tree abstract data type and applications of tree. So in the first session, the first 1.5 hours, we'll discuss about like tree ADT, how the what's the need of tree, why we have been moved on to tree, the representation of it, and what are all the various terminologies that we'll be using. And we'll see about binary and tree traversal. I have some few examples and algorithms to be discussed. And then in the second session, in the second slot of session, we'll be discussing about the applications of tree, wherein I have planned to cover. So this is my plan of presentation. And coming for the introduction, so as we all know, I'll go with slideshow. Yeah. So we all know in general with a data structure, we all know like there are two types. One is the linear, the other one is the non-linear way of presenting. So yeah. So linear is nothing but it's a sequential way. So as we can take an example of student list wherein it will be the registered number order and even it will be in the alphabet way. So this is how a sequential way of maintaining a record. So that's the linear way of maintaining a data structure. Wherein coming for the non-linear, obviously it will be of non-sequential, wherein we have a cluster of order, we don't follow any kind of order for maintaining the data that we have. So these are all the two types. So as of a tree where we are going to discuss today, it is purely based on non-linear data structure. So this non-linear data structure we are going to discuss in detail with a tree representation. So as I said this linear can be represented in memory by using one of the basic strategies. One will be the sequential memory allocation, starts from the indexing with 0, 1, 2, likewise till n-1 it will go. So we'll be following an array structure, and that's how it goes on. So each and every array will hold, each and every indexing will hold some elements. With the help of pointers, we'll try to take it out. So these structures you can go with array or you'll be going with linked list. So when generally we'll be using when we want to like operations like searching, and if we want to do some kind of sorting in an easily performing way. Why we are why they have pointed at easily in the sense because we are storing it in sequential way. So if I'm having a record of if you're having a 50 set of students which in which the register number starts with 1 to 50. So it will be follow the linear sequential way. So it is very easy to search a record which is of 49 or 45, whatever the number may be. There is no cluster order. So, or else you will be using linked list, which will be very helpful when the number of data items in the collections are likely to change. If I want to change the record which is presented in 15th location, then I can be able to easily change with the help of array indexing or even with the help of linked list. So coming for the non-linear, this is totally opposite, which is of like purely clustered, no organized fashion or no sequential way. So a data item which has a non-linear could be attached to the several other data elements to reflect to a specific relationship. In linear, as I said, we have, if A of 0 is there, then we will be having A of 1. So this 0 will be pointed to A of 1, or else if you are storing it in the array structure, then we will be having this kind of array structure, right? Whereas in non-linear, we cannot say that single one data element. The single data element can be connected in n way of elements, in n way and to n elements. Okay, so that's possible. So what we have to do whenever I want to search, I should able to find out which path I'm going to track, which path we are going to track to find that particular element. Whereas in linear, as we all know, it's very easy to search an element, very easy to sort particular element that we hold in the data structure, right? So here, as like multidimensional array, tree and graphs are some examples of widely used nonlinear data structure wherein holding to a single data element, it is attaching to multiple data elements. So if we are going on with a multidimensional array, so it will be a collection of 1D, and or else you can take examples as tree structure and graph structure. So tree is nothing but a root will be there wherein you have so many connections to all the nodes. Yes, so all the nodes will be called as linked nodes. Okay, and each and every nodes, the connection, the relationship we are going to talk about, and how the data elements has been attached to that particular root node or any kind of node in the, or any kind of internal node in the tree structure. Or else graph is nothing but edges and vertices will be there. So each edges will be representing the connections or the relationship among each and every nodes. So that will store the data elements. So these are all some basic examples of nonlinear data structure. So this is again, you can see, you can have some more examples. So imagine that you are hiring a computer database. So generally what we'll be doing, so if a company, so if any of the employer is trying to maintain their employee records, then they'll be collecting all the names, right? All the names starts, even it starts from hierarchy, or it starts from school, or it starts from department. Okay, so each and every section will have n number of employees. All those names will be collected. And what they'll be doing, if it's scope, if it's School of Computer Science, then if it's scope, how many? Say for example, 180 records. And if it's sense, if it's electrical or electronics, then how many? Say for example, 70. So all these names will be collected and they will be making it as a list and they'll perform it, right? So this is how generally before going on for tree, this is not with respect to tree I'm explaining. I'm generally explaining how we'll be maintaining a data set record. So if any institute wants to collect all the employee names, they'll go with the department wise, and with respect to each and every department, they'll collect and they'll prepare it as a table, right? This is how it will be prepared. So here you can see the employee name and the position. So with respect to position, they'll be collecting it and they'll be maintaining it as a table. And here, can anyone point out like what are the disadvantages that you will be facing when we are maintaining this as a data structure? Professors? So generally they have maintained this as a table. And here you can find so many names. And here the question with respect to each and every person is being given over here. So in general, if I'm trying to process it, or if I'm trying to search it, or if I'm trying to sort it out, we the relationship between each and every person or each and every employee. Am I right? Can we able to get the relationship between each and every person in a table representation way? Okay. So we don't find any relationship between this. So the easiest way of representation, the easiest or you can say a better way of representation whenever we are collecting this type of records. So this is how the representation should be. Because here you can see manager and the vice president is there. And we know the vice president who will be the in charge or who will be the authority of all the employees who's being given here. Okay. And we know like if there is any employee or here you can see some set of employees. So the immediate subordinate or the immediate manager. And there should be some link between these two. Okay. So these kind of relationship is being missing when we are maintaining as a list, simple list or as a simple table. That's the reason why a better presentation is being needed for maintaining this data structure and for processing it. So here you can see our presentation is being given with the connections, the relationship between each and every designation. So vice president, so the superior hierarchy or like the authority will be the president. And then you can see the vice president, the immediate subordinate is manager, and finally the employee. So this employee know to whom we can able to whom we have to report it. So this kind of representation is most needed. That's the reason why we are moving on from a simple list structure to a complex, or you can say, yeah, even the tree is also simple. But then we are talking, we have this is non-linear because no sequence. Here you can see none of the sequence is being followed. There is no alphabet order, there is no number order, there is no indexing order, nothing. It's being clustered up, it's being put up together with respect to the destination, right? Designation. And then coming for the data structure. So if this is a general example. When we are coming for data structure, so how we are going to represent this, what is the point that we have to follow, what is the principle that we have to take it upon. So that's what here you can see. So this is a simple general view of a tree. Generally, don't think about data structure. Generally, how we look into a tree. So generally, the root will be in the down, okay, and the branches will be upper side. The root will be in the bottom side. But when we talk about data structure, the point or the view of a data structure point of view would be quite different. Here you can see the root will be in the top. So where we have to process, where we have to begin the process in the sense, we have to start it off with root way. So the root will be processed first. Then you can see there are so many leaves which has been there, and we have to take it, yeah, branches. And this branches we are going to take it off. So this is one branch, this is one branch, and this is one branch. And here you can see each and every branch will have nodes. So this is how a view of tree in the data structure point of view. So coming to the introduction of tree structure. So here it is, again, I said, this is a hierarchical order data. So it is of purely non-linear. You can say an example of common example, which is of employees of an organization, or else you can say the common system folder that we have, because we are not following any sequential way or not. So that's again, that's hierarchical order we'll be following, but not with sequential, right? So these are all some examples. And coming for the applications of tree, yeah, nowadays in AI and gaming, it's moving. And searching, yeah, there are so many tree applications we are going to discuss, or else in directory to maintain a system directory, even in Java, you all know. And yeah, compiler parse tree, sorting, and database indexing. So for all these are all the basic, very basic applications wherein which this tree has been used. Now again, here you can see another one example. So here you can see tic-tac-toe game. It's another one tree representation example. Here you can see the example. Okay, so we all know this is a 3x3 wherein diagonally if we get this X, okay, so the whose will be the winner. Here you can see this is the diagonal way. So this is one diagonal. Okay, so this is how we used to play. I hope you all know about this game very well. I think like everyone have played it. Okay, so this tic-tac-toe game, it's we all know this is a great entry point to understand the game tree for many reasons. So here it's a two-player game. So say for example X and Y. Okay, so it's a two-player who is going to win, loss, or it may go with draw. So this is the simple snapshot between player X and player Y. So there are two players. It's a two-player game, X and Y. So it depends, purely depends on the move. How does it takes? So how the X taking and move, how the Y is taking on the. That's how it happens. And here you can see -1 +1 were there. -1 +1 is nothing but the favorable outcome of player X. If X is moving in a favorable way, then that is +1 scenario. Or else if -1 in the sense that depends on, that's for Y. So if X is taking a positive move, then that is +1. If Y is going on with a positive move, then that is -1. That's the reason why they have given us +1, -1, and 0. 0 is mean neutral. Okay. So here, player X, here you can see player X is trying to maximize player Y. It's trying to minimize, which means, yeah, if, in every two-player game, we all know, yeah, we have to win. I have to win, or you have to. No one will say like you can win. So what they'll do, they'll try to maximize their outcome. So if Y tries to maximize, then the -1 will get increased. If X tries to maximize, then this will go on increase, right? So finally, they'll be getting this X position. So diagonally, they have to get this X. So here you can see diagonally, they have to move on and they have to get this X. So that's how. Why I'm showing this example? No, this is a basic tree representation example. Here you can see wherein the two players are trying to maximize their outcome with just by representing or with just by a move. Very like known example for tree representation, wherein we can have so many outcomes with the move that we take. So generally, we in data structure, what we'll be doing with the help of tree, we'll be doing sorting, we'll be doing traversal, we are doing so many things. So for each and every operation, we'll get some set of outcomes. And the outcomes, we have to check whether the time complexity is fine, whether even though we are moving on for binary tree or AVL tree, there are so many applications, right? So we have to make sure like whether this has been getting a positive way or whether this has been getting so much pros over the previous one. So that's one example, this TikTok. And here you can see the defined set of definition for this tree. So tree is nothing but a finite set of nodes, one or more nodes. So here you can see this is the root. So the root is having a subtree sections. So R1, R2, R3, R4. So this is T1, T2 subtree, and T3 and T4. So here the nodes are partitioned into n greater than or equal to 0, disjoint set. All these are disjoint. So T1 to Tn, where each of the sets is Tn, are called the subtrees of the root. So this T1, T2, T3, T4, all these are the subtrees of the root. Coming for the terminology, yeah, tree has so many terminologies. So when we are going on for operation, we have to make sure like terminologies we know in the right way. So node is nothing but the information to each and every node. So here you can see this is one level, this is another one level, and this is another one level, wherein this A, B, C, D, the information, the item of information in each and every tree is the node. And children, so the subtree of each and everything. Here you can see A is the root. Okay, so these are all the subtrees, and B, C, D, E, F. So the children of C is E and F. The children of A is B, C, and D. So likewise, parent, we all know, like A is the parent of B, C, and D. The reverse. When we talk about children, the reverse is the parent. And root, it's a separate node. It's a distinguished node, usually drawn at the top, and it has no parent at all. Okay. So the root will have no parent, and the leaf node will have no child. That's what the basic rule. The root will it will not have any parent at all. So if all the children were null, here you can see B, D, E, and F. These four don't have any children, then that is called as like leaf. Otherwise, it can be called as, so this C is called as internal. So this is node. These are all some nodes. When we talk about internal, so the other one, the one which you are left out with leaf node, the left nodes are called. This is the child, and this is the parent. This is also a parent. So these are all basic node definitions. And next is siblings. Siblings is nothing but the children of same parent. So here you can see A is a parent of B, C, and D. So B, C, and D, the parent is A. So it will be of siblings. And the path in the tree, so you can see if I want to travel out from A to E, then you can go with this link, right? This link you may take. So this is the path wherein how we are following. So the sequence of nodes such that adjust. So make sure UI plus 1 exist. Okay. If you are traveling out from UI to, if I'm going on with 2, then 2 plus 1, 3. So if the edge exists, then we'll take the path. Otherwise, we'll go with the next one. That's it. So it's a connected acyclic. Here you can see it's been connected, but it's not a cyclic graph. And ancestor is nothing but node U is the ancestor of V if there is a path from U to V. Say, for example, if it's of V, if there is a path from U to V, then this is called a ancestor of V. If it is a descendant, then that's a reverse. A node U is a descendant of V if there is a path from V to U. If you have V to U, then it is called so ancestor and descendant. So here you can see a simple example, ancestor of G. So G, here you can see there is a path from, so F to G, it's there. So obviously it will be of F. So E, here you can see descendant. So there is no reverse path. So it's of F. So here you can see from F you to G you have a path, and whether H is ancestor of I. So here you can see H, and H is, because we don't have a reverse connection over it, no direct connection because the direct edges should be there. So that's the there is. And coming for the subtree, here you can see subtree is rooted as U. It's tree formed from U and all its descendant. So this is one section, and here you have another one section of subtree. And here when I talk about A, so these are all the 3 sections of subtree. So coming for the degree, yeah, degree is nothing but the number of subtrees of each and every node that you have. So when I talk about A, here you can see 1, 2, and 3. It's 3, right? When I talk about B, it is 1 and 2. When I talk about K, there is no section, there is no subsection. So it will, it's a maximum number of degree of the nodes in the tree. When I talk about degree of node, you can actually calculate by this way. When we talk about degree of tree, which is the highest element of the highest degree of each and every node, it's equal to the highest degree of the tree. So obviously it will be of A. A is holding the maximum degree, which is 3. So the degree of the tree is 3. So next is height and depth. Because without knowing all these terminologies, we cannot go on with the operations. So that's the reason why I'm explaining all these. And next is the height. Height is the longest path that you have, that you are following to reach out the leaf. That's what the highest path. And depth is nothing but the length of the path from root to U. If I'm taking any node, so how far I have to go from the root, from the top of the node to the end. So how far I have to go with respect to each and every node. So here you can see the difference. The height is with respect to leaf. The depth is the node which we are trying to reach out. That's what U. Then height of the tree is equal to maximum depth of the depth of its nodes. So if I have the maximum depth, here you can see the depth is 3. So that, and a level of node, a level is nothing but the measured distance from the root. So how much I have. So here you can see this is the depth. So depth 0 because that's a root node. So obviously depth will be 0. It will start from 1. And this is the next level, which is depth 1 and depth 2 and depth 3. So when I talk about depth 2, if I want to reach out this particular node, you will be following this one, right? It will be of 2. That's what? That's the depth. If I'm taking height, so height, what is height? From root till the end of leaf. Till the end of the leaf in the sense, till the end of depth, which is depth is equal to 3. So from height till here I'll be reaching. That's what the height. So this is how we used to measure the depth, height, and level and all. So these are all some questions. A node with no parent is obviously root node. I hope you all know. How many edges are there in the tree with n nodes? Any idea? How many edges are there in a tree with n nodes?
And n minus 1.
Yes, exactly. N minus 1, because here itself you can take 1, 2, 3. Okay. And here you can see the total number of nodes. So this is how n minus 1. And how many path exist from root in a node of path exists from a root to node in a tree. So generally we have two, okay, two in the sense like two path and two parents. So exactly we have one path from root to each and every node. If we have two paths, because in the previous example we have two, okay. So some node along with two paths will have two parents. In general, we have one path, okay. So these are all the basic properties of each tree representation. And here now we are getting inside into the data structure. So how it's actually represented, because this is a tree way. But when we talk about the logic, when we talk about the processing, when we are doing it, when we are coding it, so the process is totally different. So that's what here you can see. Okay, so this is the tree representation. Either you can represent in a linked list way or in array way. So both are possible. But here you can see in the linked list representation, it starts from 0, 1, 2, 3, 4, 5, 6. And it goes with, here you can see A, B, C, D, E, F, G. So which is being ordered, which is being written here. And A doesn't have, and you have another section called as parent and child. A doesn't have anything. So parent is not there because it's in root node and 0. So where else it's been pointed, because we have to represent the linkage, we have to represent the like relationship between the nodes to other nodes. So A is having a relationship over B and with a relationship over C. And B and C, we know the number is 1 and 2. So that's being presented over here. And then C it's having with G, where else next we have to start off with B. So B is having a connection with D, E, and G. Here you can see 3, 4, 5, it's being connected. Whereas C is having a direct connection with node 6, which is called as G. So here number 6 is being mentioned. And the rest of the part are not having, because all these are leaf nodes and they don't have any connection at all. So which is being given as null. So how we have to represent as a structure, here you can see, so all these will be presented as a structure. One thing is the data that we all know, A, B. And we have three sections. One is data, the other one is parent, the third one is child. So we have to give the reference of parent and child of each data. So once we talk about the character data, character A, so we have to talk about, here you can see, if it's of character A, there is no parent, but then I have to make the child references 1 and 2, which is called as B and C, right? So that's what the structure node parent and child reference address is being given with the help of pointers. So this is how the general simple tree representation would be written in the data structure way. And if I'm having the left and right sibling in directly in the list itself, then how we have to represent? It's again a very simple one. So left child, it's there, and right sibling, if it's there, then you have to give, otherwise it's null. So here you can see left child and right sibling. Okay, so you all know siblings is nothing but which is coming from the same parent. If it's not there, then it will be of null. So how do I have to extend this structure? It's again very simple. You have to represent the data, then the parent, then the left child, and the right sibling. So this is how the representation would be. Now coming for binary tree. So far whatever we have discussed is very simple basic representation of tree and the terminologies. Now we are moving on for the first section, which is called as binary tree. So binary tree, again a non-linear type, which can have almost maximum of 2 children for each and every parent. It has a left and right reference along with the data element. So each and every one will be having a. And what else? The node at the top, we have, which means the root node. Of the hierarchy of a tree, it's called the root node. And the node that hold other subnodes are called the parent nodes. So which has the other subtree, which will be called as parent nodes. So parent and the root. So that we'll have. And at most 2 non-empty subtrees we have. Maximum of 2 it can have. And then in which each and every parent node in binary tree can have at most 2 children, as I said. So one is the data item. The first one is the data item. And second one is the address of left. And third one is the address of right. So address of left and address of right. That's it. So here you can see some example of it. When coming for the classifications of binary tree, as I said, it will have at most 2. So 0 to 2. A binary tree is called as full binary tree. A complete binary tree in which every level except possibly the last is completely filled with all the nodes as with left and right. So the last nodes are alone, you can leave it. Otherwise, you have to fill it off. And if all the D levels, if all the depth levels of the height of the binary tree are filled, then the tree is called as perfect. Okay. So we have 3 classifications. So all these 3 classifications are called as binary tree. So you can have at most 2 or either 1 or 0. That's what, at most 2. So here you can see a root and the left and right. Here it's having left and right. And here it's having left and right. So this is full. Okay, this is full. And then when I talk about complete, we all know the last alone, we cannot be filled with left and right, whereas the rest of the node should be filled with left and right. So here it's on the top, left, right, everything is being filled. Since last leaf nodes is being done. Here also last leaf nodes we are trying to stop. And here, if a binary tree is called as perfect binary tree, then all the height starts from top to depth level. So all these levels has to be filled off with left and right. So here you can see this road is having 2, and the left is having 2, the right is having 2, and each and every node is having 2. Because we have totally 0, 1, 2, 3. So till the 3 levels we'll be having. So how many nodes in the last depth of 3? 2 to the power 3, which is 8. Okay, so this is how you will be calculating. So these are all these are termed as binary tree. You can go with either any of the binary tree. So it depends on like what is the problem that we are taking, or what is a like problem that we are trying to do. Okay, so we have to first make sure whether it's full, complete, or perfect. So here you can see some more examples. Full, because it's not complete, because we all know complete in the sense last alone cannot be filled, but the rest has to be filled. But then here the first itself it's not filled, and then here you can see it's again complete, but it's not full because it's been not completed, and neither complete nor full because you have only one wherein this is not even having left or right in the first level itself. And full and complete, yeah, only we have 3. This is full and complete, we can see. And here also you can see, and this is complete and this is fully perfect because till the last node it's been done with left and right. And here we can see from the picture itself, we can see full, complete but not full. And here also you can see complete and full because we have only 3. And here you can see the last nodes alone, the last leaf nodes alone, it's being not completed. So complete because and it not full and not perfect. Okay. So coming for the properties of binary tree, when we are constructing a binary tree, what is the property that we have to check it on? So one is like, if it's a full binary tree, number of leaf nodes is the number of internal node plus 1. So we all know what is internal node, the one which we are lefting out with root and one which we are lefting with leaf. So the rest of the nodes will be called as internal, right? So this is internal plus 1. So where L is a number of leaf nodes and I is a number of internal nodes. So here you can see these are all leaf nodes, right? So these are all leaf nodes, you all know. So here you don't have any child at all. So here you cannot take, right? So the rest of the nodes will be one would be the like leaf nodes 1, 2, 3, 4, 5. Okay. So the rest of the nodes, I mean internal node is 1 because we have only one internal node. The rest are parent and this one, and that is 6. And the same way here also you can see 0, 1, 2, 3, 4. Okay, so number of leaf nodes you can see 2 plus 1, which is 3. Okay, so this is how you have to calculate a number of leaves in the node. How we will be calculating how many leaves I can able to have it in a binary tree. And this is one property theorem which is being proved. Okay, so the first one is the non-empty tree with 0 internal nodes has 1 leaf node. The non-empty tree, which is a binary tree, and we cannot say that is a perfect binary tree because they are saying which will have only 1 leaf node. So obviously it will not be a perfect, but either it can be a full or complete. Okay, So with 0 internal nodes, which will have only one leaf node. A full binary tree with have only one internal node has 2 leaf nodes because it has one internal node. So obviously what it can have 2 leaf node because it has to satisfy the binary. And if it doesn't have any internal, what it has, okay, so from root it can have, so that's the reason it has only one leaf node, and it can have 2 leaf node from this. And that's the base cases for n is equal to 0 and n is equal to 1, we have to conform to the theorem. So this is non-empty tree. This is the theorem they have given for binary property. So the hypothesis they have made, all these are proven concepts. The hypothesis they have made is assume that that any full binary tree containing n minus 1 internal nodes has n leaves. Okay, if I have 5 leaves, then I'm making sure 5 minus 1, 4 internal node n. The same formula they have used. That's it. The same formula, since they want to calculate the internal node, they made it as L minus 1. That's it. Okay. And what are the steps to prove this theorem? Like I have to prove if it is 0 internal node, it should have 1 leaf node. If it is 2 leaf node, 1 internal node, then it should have 2 leaf node. So what's the way of like proving it in the sense? Given tree with n internal nodes, you can see a tree is being given, okay, the T with n internal nodes. Internal node I whose children were both leaves. So which means internal node, they have n internal node in the tree, and they are having, because n internal in the sense, say for example 5 internal, no, so they are taking only one internal node whose children are both leaves. So this is leaves 1 and leaves 2, and this is internal 1. So remove both the children of I, making I a leaf node for the new tree. So they are removing both the children, it's been removed. Now what I will become, because I don't have any children, so I will become the leaf node, right? I will become the leaf node, and this will be a new tree. So they are making, so from T, from the actual tree to this tree, just to satisfy the theorem, just to prove the theorem, they are going to take this way. And now T has n minus 1 internal node. What is the reason? Because one has been already removed, one internal has been already removed to leaf. That's the reason why it is having n minus 1 internal node. From induction hypothesis, T has n leaves because that's what given. T has n leaves. So here you can see. Now restore I has 2 children. Now T has n internal nodes. Yes, of course. If I want to restore it, which is being deleted, obviously T will have n internal nodes, right? From n minus 1 to n. So how many leaves does T have? So at the end point, T will have 2 children, yes, which will have n plus 2 leaves, but the internal will be counted so as n minus 1. So here the theorem is, if I have 0 internal node, which means I don't have any internal node at all, then the leaves will be 1. That's what we have seen in the second and third step. And then if you have with one internal node, if it's complete, if it's a full binary tree, don't go with complete. If it's a full binary tree, then any internal node, say for example I1, which will have 2 leaf nodes, okay, and any tree which you are trying to like before deleting it or before trying to restore it, it will have 2 children, which yields n plus 2 leaves because it has an internal node n, and but it will be counted as n minus 1. N minus 1 will be the total number of internal nodes with respect to the leaf. So this is how a property has to be proved. Even you can apply this, you can take some example and you can apply the concept. This will actually work. And all these are some notations that we have to calculate with respect to perfect binary tree. So perfect binary tree, as we all know, till the depth of the level, it will be complete with left and right. That's what perfect. Then if I want to calculate with any level, if I want to calculate with level 0, 1, 2, then I have to go with the formula of 2 to the power level, which level I'm in. So if it's of level K, so if it's of 2 to the power 0, then I'll be having 1 node. That's what you can see here, 2 to the power 1. Okay, so which is 2. This is level 1, and 2 to the power 2, 2 to the power 3. So the same way, if I want to find out the total number of nodes, you can use this formula. So from the topmost level, it will be calculating. So 2 to the power 0 plus 1 plus 2 plus 3. That's what. Very simple. So how many leaf nodes you have? Then that is 2 to the power h, because leaf nodes in the sense I have to go with the last level. So where I'll be finding the last level? Obviously the height of the binary tree, it's the last level till it reaches the end level, end depth, or the height will have the measure. So that's the reason why they have. And then how many internal nodes I have? So internal nodes in the sense you have to subtract this height alone, right? So from the total number of nodes that we have calculated from this, you have to subtract 2 to the power h. That's it. So this is how the calculation made, and the geometric series here in the last one we have seen 1, 2, 4, 8. So how it's been represented in a geometrical way. So number of nodes in the perfect binary tree which can be calculated in the same way, and the same example is being given here. I have taken the same example. So again, how the proof would be. So as we all know, a perfect binary tree has the height of 2 to the power h plus 1 minus 1 nodes. Yes, by induction, how we are taking n of h be the number of nodes. Okay, if the height of the binary tree is h, so the total number of nodes they are taking. And the base case they have is if the h is 0, then if the height is 0, then obviously it is a single node tree, right? Single node tree. So 2 to the power 0 plus 1 minus 1. That's what, which is of 1. And then here you can see, because it is 2 minus 1, which is 1. So since the height is 0, we can directly go without even calculating. We can go, the total number of nodes will be the single node since the height is 0. Say for example, it belongs to 0, I less than. So the value that we are taking here for calculating the number of nodes is respect to which will fall between 0 and h. Okay. So the perfect binary tree will have two perfect binary trees of height h minus 1 plus 3. So if the h consists of two perfect. So here you can see 2 into n of h minus 1. Since we don't know like how many like perfect tree which is being given, if a full perfect tree which is being given to you, then into n of the number of, n is nothing but the number of nodes in the height of the tree, which is the height is h. So n of h minus 1 plus 1. So this one, do you know the formula? Because you'll be applying this 0 plus 1 minus 1 that will be applied here. So 2 into 2 to the power of h minus 2. So the total height will be calculated. 2 to the h, which nothing but the leaves of the final one, and 2 to the h minus 1, which will be of internal. So this is how we can directly give this formula, but then we should know like how this has been arrived. That's what this slide will talk about. So how from the formula, how they have been proved, 2 to the h will be the leaves and 2 to the h minus 1 will be the internal. And yeah, the same form, the same explanation, but then along with the how much time it will take. It's been given here. The proof is being given here. And here you can see one sample exercise of we can give it to students while we are handling this course. So the height of the tree is the length of the longest root to leaf path in it. Yes, we know. The maximum and minimum number of nodes in a binary tree of height 5. So they have given height as 5. We have to find out which should be of minimum and maximum that will follow the binary tree principle. Any idea? Okay. Here I have shown the example itself. So height, we all know which has been the longest route, which starts from the root till the path, till the leaf, through the path. Okay, and they have given us 5. Okay, and they have given us 5. We just discussed one example, which is 2 to the power h plus 1 minus 1. So what is the height? Which is 5. So 5 plus 1 minus 1. So 5 plus 1 in the sense 2 to the power 6 minus 1, right? 64 minus 1, which is 63. So what is the maximum node that I'll be getting? Which is 63. And next, we all know the minimum. Minimum is nothing but the level that we can take, since they said it as 5. Okay, 5 plus 1, which is 6. So here you can see the options 64, 5. Obviously, it will not be the divisible of 2 because we have 2 to the power h plus 1 minus 1. So obviously 64 will not be there, and you can eradicate 32 and 31. So the competition will be there between the 63 and 31. Am I right? So 63 and 31 in the sense, since the height 5 is given, the number 5 is given. So 2 to the power 5 plus 1, which is 6. So obviously we have to go with this option, which is 63. And coming for the level, since they made it as height 5, there may be left skewed. Okay, the tree may be skewed, and that's how they can draw it. So this is one exercise which we can share it with students as well. And minimum number, as we all know, minimum number is nothing but the levels plus 1. So what's the height level? That's being given. Since we have to calculate with the top, so height, the number of levels plus 1. Since the height is being given as 5 or 6, whatever it may be, that has to be added with 1. That's the minimum node in your tree. And yeah, coming for the other representation, so we have seen some more representation of binary. The other representations of binary were left skewed or right skewed, which you have, or else you can call it as degenerative trees. The right side will not be there, or it has no child, only the left side will have the extension. That's called as left skew. And the right skew would be the right side alone you have, the left side will not be represented. So these are all some degenerate and balanced, perfect. All these you can see, or all these we have just discussed. And how we are representing it, because the construction of binary. So now what we discussed, how we have to draw it and how we have to what is way of representation. But then when we talk about data structure, we have to know how we construct a binary tree. That's most important, right? So before constructing, we should be clear about the representation way. So here, for example, I have taken this as array. Okay, array representation, which like focus on, assume it's starting with indexing 1. So indexing 1, 2, 3, 4, 5, 6, 7, likewise it will go on. So it will follow this order A, B, C, D. So till the data of all the nodes will be represented. And then 1, 2, 3 will indexed. So how I will be, if 2 to the power I, sorry, if 2i, if the total size is the index size I'll be taking, and less than or equal to n, which means a number of nodes, then you have to go left of a. Otherwise, how I'll be going with right of a? Because this is 1, this is 2, and the index 3. So in array, we don't know, like we cannot go with directly with C. We can go with index, right? So how I have to go? Which is 2i plus 1. 2 into 1 plus 1, which is 3. If it is 2, 1 into 2, then I have to go with left side. Okay, directly with the index question. So that index question, they have made that as a formula, which is again very, very simple. So 2 into 1, which is less than or equal to n, in the sense you'll be going with left. Otherwise, it will be of right. Then for parent, how do I go? 2 by 1, right? Sorry, I by 2, which is like 2 is the index position. So 2 by 2, which is 1. So if I want to go with like from 4, so 4 by 2, which is 2. So which will lead me to go with parent, right? So this is how we have to go. This is the representation next in. And here you can see the example of it, 2 into I plus 1, 2 into I plus 2. This is how it goes, array implementation. And these are all some examples. Each node in the binary tree will be represented as the data left and right. And here you can see the data left and right would be represented. And there is another one tree called as n array. N array is nothing but which will restrict the number of children of each node to 2. Because there we can have at most 2. If it's of n array, then we can have, it will be a restriction of, we can have as the children will be of each node should be of 2. And restrict the number of children to n. And if it's of 2 array, then it will be of 2 children. So here you can see ternary and quaternary. So it will be of here each and every one. It's 2, 2, 3. Okay. And here 1, 2, 3, 4, 1, 2, 3, 4, each and every, that's a 4 array. So here you can see each and every one will be having 4. So these are all some other classifications which we have inside binary tree. So how would you be calculating the levels? So if n array tree, each node has n children or no children, then the wholes n minus 1 into I, the internal node, plus 1. So this is the formula. Directly we cannot go, since Here, if it's of ternary or if it's of two array, it will have two, or either it will have no. So we cannot directly stick on with an example of 2 to the power h minus 1 or like 2 to the power like h plus 1. That kind of formula we cannot directly apply since it differs with each and every node, right? So that's the reason why this kind of formula has been given. So now we are moving on for the tree traversal. So the operations we are going to perform with binary tree, and we are going to like see one example with respect to the tree traversal. So as we all know, the representation alone is not enough. We have to perform some operations. So that operations how we can perform. So here, when we traverse a tree, each element of the binary tree, we have to make sure each element of the binary tree is visited exactly once, because if you visit more than one time, then the complexity would be high, right? So during the visit of an each element, all action, whether we are displaying, whether we are evaluating an operator, whether any expression has been given to evaluate. So with respect to this, the element has to be taken and we have to visit it and we have to make an action of it. In general, we have four traversal methods. One is pre-order, in-order, post-order, and double order. So these are all the four orders. So here you can see some example of it. So the example of tree representation, I need some kind of expression and that's been represented as a tree. We are going with each and every order. So first one, pre-order. Pre, so from this we can say, pre in the sense the root has to be visited first. And then left, then right. If it is in, then we have to visit, the root has to be in the middle. It should be in between right, left and right. So travel. And then post in the sense, finally, after visiting left and right, we have to visit the root finally. So traverse a left subtree, right subtree, and finally the root. So this is how we have to just visit all the roots. This is how the order of traversal follows with respect to pre in the sense, initially root, in the sense, in between left and right, the root should be visited, and post in the sense, finally we have to visit out. And here you can see pre. So obviously the root has to visit first. So A, and then left node and right node, which is of B and C. And here pre-order example is being given. You can see, so first the root and then the left subtree and then the right subtree, right? So left, right. So how do I go? With A, with B, D, G, which is H, and then you can have other left side, the entire left side of A I'm talking about. Then E and I, that's been visited, that's been traversed. And then you can see C, F, and J. So this is how you have to visit. I'll just write an example and I'll show you how we have to. One sec.
Ma'am, thank you so much for the session, ma'am. Participants, if you have any doubts, you can ask Subbulakshmi, ma'am.
Ma'am, actually, I didn't complete it. Like I stopped sharing and again I'm sharing it. If you want break session for now.
No, ma'am. I thought you are just leaving a break as of now.
No.
Problem,
Till
ma'am.
10:30 I'll take.
Okay, ma'am. Okay, ma'am. You can continue, ma'am.
Because I just want to show an example that.
Yeah, okay, ma'am. Okay, ma'am. Sorry for the interruption.
That's fine. That's fine. I'll show an example how this traversal works on and how we have to construct a binary tree from after doing this. So first one, tree traversal. So first I'll take the same example A. So B. G H, and we'll have this as right side because in the example it's being given such. So I'll go with the example and I, and for F again the right side node which is J. So this is what it's being given. So right, we have to go with number. So 1, 2, 3 because it's left side and right side. So I'll go with this order, and 4, and then we have to complete this tree which is of 5. Then we have to complete this one because once we are done with this, we have to go with B and we have to complete it. No, so this is 6 and this is 7 and this, yeah, this is the left side is done. Since first initially we are going with pre-order, right? So pre-order in the sense root is the first one and then left side and right side. And coming for the right side, so it is of 8, 9 and 10. This is how indexing happens. So now pre-order, root, left, right. Okay, so root, left and right. So how should I have to write? So first one root, which is of A, next is B. You can go with the numbering order, then D, then G, then fifth one is H, then E, I, C, F. So this is how it happens. So we'll be completing. This is the root node, and till I, this will be the left side node, and this is the right side node. So which is being traversed. And then post order, pre-order, post order, in order. So post order, post in the sense we'll be visiting the root last. So left, right, and then finally the root will be visited. Right? So here you can see first one left in the sense the left has to be visited. So what's a left? So this is how G, because it has to be traversed. No, so in the top, the down, G, H, D. So the last one is done. And then where we have to come? We have to come with I. So I, E, B. So the left is done now. Next we have to come with right. So what's a right? J, F, and C. J, F, and C. Then finally we are visiting the root. So this has been traversed initially. That's the reason why G came first. Then we are traversing the right and finally the root. Okay. And then the third order. Third order is in order. In order in the sense left, root, and then finally right. So what's the left side? So left side is same. G, H, D, I, E, B. Right? And then root. Root is A, and finally the right is F, I, C. Okay, so these are all the right. Sorry, F, J. F, J, C. So J, F, and C. So this is left, and this is root node, and this is right. So the left traverse will happen, and then the root node, and then right side traverse will happen. So if we want to construct it after traversing, we have to construct it no, because we need to do all the operations. We have to search it, we have to scan all the elements, and we have to construct a full, complete or full binary tree, right? So for example, I'm taking the same example I'm taking for binary tree construction. Okay, so first one and then pre-order. Say for example, these two has been given and you have to, the same example, watch what we have taken, I have just represented. H, B, E, I, A, F, J, C. This is the in order, which means in order in the sense root has to be in between left and right traversal. And then pre-order, A is the root. In pre-order, we all know the first one is root. And B, D, G, H, E, I, C, F, and J. This is the pre-order. So all these still left and these are all right. So when we are trying to construct a binary tree, we have to fix off the root element. Since we know the pre-order, we know the first element should be the root element. So A is the root. A will be the root. So I'm fixing A is the root. Okay. So A is being taken now. So A, here you can see A is being fixed. So we are locating A in the in order root. Okay. And the left subtree we can go with G, D, H, B, E, I, and then I'm fixing A as the root element and F, J, C. So this is right and this is left. Then what we have to do? We have done within the construction, we have done with only one element which is of root. Then we have to fix off with left side and right side. So next we have to scan the second element because one by one alone it will scan. You all know since with array representation we have started. So only one element it is going to scan. So the second element we have to scan it. What's the second element? It's been given here, B, right? And we all know B is being represented where? In the left side. From the order traversal, we can see. So what we have to do? A, we have scanned the second element. Since B is being there in the left side, so we are representing that in the left side of the tree. Then what we have to do? In the right side, what we have? F, J, and C. And in the left side, again we have, again you can see, no, this B will become the root and this is the right side and this is the left side, right? Since I'm taking this as, I'm not writing this as a node structure because this will be not as a single data representation. Since we are representing as a whole, I'm not representing this as a node. And here you can see E, I. Okay, so this is the second step. So this is the step one, and you all know this is the step two. So now we are done with the second scan element. Next, you have to do the next one, scan the third element. So what's the third element? In the pre-order, we are going to scan the third element, which is of step 3. Okay, so A is the root element. Now we have fixed off with 3. And then we are scanning the next element. So the scanning the next element in the sense you can go with D. So because D is the one which is being represented in the left. Think this D, if we are fixing this D, then you can see this is the left side, this is the right side, right? And in order, so this is the left side and this is the right side. So we'll be representing this 3 in the third scan, and we can make this G and H as the right side and the left side, sorry, left side and the right side. So I'm making D and then G and H. Now we can make it as a node, single data. But then we were not done with the right side of B. So since we have E and I over there, I hope I'm right. Yeah, E and I over there. And then in the right side of A, we have F, J, and C. And then again, we are going to scan the fourth element in. So the fourth element, we are done with B, D. Okay, next we are done with G, and next we are already done with H. So next we have to go on with E. So where is E? E is again there here. Okay, E should be in the right side of B. Okay. And we have to make, so how should I write? A, B, E, G and H. And then E should be in the right side of B, no? So E, and you all know, like again, it should be in the E, and next is I. So obviously it should be in the right side of E, right? So here you have to write the right side of E. Okay. And then the right side of A is not yet processed. So I'm directly writing it F, G, and C. Okay. And then the fifth one. Fifth one, next element we have to search. Next is obviously the leftover one is. So what else is left over? Till I it's done. So we have C, F, and J. C. So the next element should be done is C. So check in the pre-order. The C is there in the right side of A. And in the left side of C, you have F and J, right? In the right side, we don't have any child at all. So we can directly write A, B, I, and then I have C in the right side of A. So in the left side, you have two nodes, and you don't know like F and J. C is being processed. Next, what is the sixth step? Go with the pre-order, check it. F and J is being remaining, and C we have already done. And in the left side, we have F and J. So which node I have to start off with? F. So if I take out F, the right side of F is J, right? The right side of F is J. That's it. We can complete it. Once F we take out, you have to represent it in the right side way. D, E, H, and then I. And on the right side, you have already represented C. So again, I'm telling F I'm taking out. In the right side of F, I have J. In the left side is already A. That's the reason why I made it as this one. And in the right side of F, we have J. So we are making, and with C, it's been left side. No, with C, the F has been left side. And in the right side of F, it's J. So I have to write F, the right side of C, and in the left side of F, it is J. So this is how you have to construct a binary tree from a pre-order traversal. So once you find the pre-order, once you're done with the root element, next we can directly go on how to construct it. So go with the pre-order structure we have. So every time go with the structure of it, make it out the root, left side and right side segregate it, go with the tree structure, and in each and every step, it has to scan an element. So how do I find which element to be scanned? Obviously, in the pre-order, you have to check on first is A, next is B, next is D. Likewise, you have to go finish off all the elements, put it as a structure, construct it finally. So this is how a binary tree works. Is it clear? Okay. So here you can see all the examples in order example or whatever the example that we have seen. If I'm squishing the projection by in order, how does it look? Because in order, you all know at the top, I can see the root. So this is how the squishing happens. Yeah. This one, just a pseudocode representation. Here you can see a code snippet of in order traversal. So in order, root shouldn't be null. Anything, the root shouldn't be null. If it's of in order, then root should be the root to left side, then visit root, then the root of right child. So visit the left side and then the root, visit the root and then the right child of the root. The same way, if we are going on with post order, then obviously the root should be the last, okay, post order. And for make sure everyone shouldn't be null, when we are coding it, we have to go, we have to check on this. So how should I able to find the final when I'm trying to construct it? How should I able to find the like height of the tree? So I have a temporary variable. Initially, it will be of null. So I'm trying to, so each and every step I'm trying to traverse it. If it is left and if it's right, if it's not temp left and if it's not temp right, then which means I couldn't able to find out the tree, which is being stopped. Otherwise, you can have a function which will do the calculation of, which will fix it out the node of left and the node of right. Okay. And here you can see a ternary expression which will helps you to find out whether I'm reaching the final node or not, whether I'm reaching the leaf node or not. Because till you reach the root node, it has to be the same function has to be repeatedly called, and it has to calculate, and it has to fill out the left and right node. And finally, it has to return the number of nodes, right? So this is how a height of binary tree after construction, it can be like calculated. And level order, yeah. So here you can see a pointer which has been pointed to the root node. So obviously it shouldn't be null. Visit node pointed by a pointer and puts children on a FIFO queue. So first in first out queue, it will be placed all the nodes after visiting the root node, which is being pointed by the pointer. And if the queue is empty, set it will be null because I don't have any other rest of the nodes to be processed. Otherwise, delete a node from the FIFO queue and call it as pointer. Because first I have A, then I have B, C, D, E. Assume this is the tree. So initially, the tree root will be of null. This will be of PTR. Okay. What they are saying in level order, you have to take this and you have to insert in FIFO queue. So once I'm inserting it, after doing this level order traversal, what do you have to do? You have to take it out and set the pointer is equal to null. Okay. And then you have to process with the next one. So likewise, you have to go and traverse, you have to go and visit all the nodes that you have, make it as a queue, and get a node from the queue once it is called. And that, so initially, PTR will be pointing A. Then after doing this queue, then I have to PTR, it should be FB. Likewise, it has to go, and the level wise, it has to complete it. And here you can see. So as we have seen the construction, so how the construction example. So here, all these with the example I have just explained, you can check out the definition from these slides. So pre-order, post-order, and in order, if it's of level order, how does it happen? And this is one kind of exercise which we can share it with students. And yeah, so that's it. In the next session, we can discuss about the applications of tree. Ma'am?
Ma'am?
Yes.
Have you completed, ma'am?
Yes, ma'am. Yes, I have.
So if participants, if you have any clarifications, please do ask. It's a query session. If you have any doubts, please unmute and ask, or please do post in chat box. So thank you, ma'am. Thank you so much for your valuable input, ma'am.
Okay, ma'am.
Thank you, ma'am.
I can join by 10:45, right?
Yes, ma'am. Yes, ma'am. Yes, you can join by 10:45.
Okay, ma'am. Thank you.
Thank you, ma'am. Thank you. Participants, you can join by 10:45. Take a break of 15 minutes and come back by 10:45. Thank you, ma'am.